Hello folks, in video 1 of 3 for Unit 3 of Balancing Redox Equations, I discussed an algorithm that you can use to balance redox equations in acidic and basic solutions. In this video, video 2 of 3, I'm going to show you an example of balancing a redox equation under acidic conditions. In this example, we're looking at permanganate MnO4- reacting with an iodide ion, I-, to make manganese 4 oxide, MnO2 solid, plus iodine gas. In step number 1, we break apart the unbalanced equation into the half reactions. Here you can see that the manganese is changing its oxidation state, and the iodine is also changing its oxidation state. So these are the two half reactions of interest. MnO4- going to MnO2, and I- going to I2 gas. In step number 2, we balance all elements that are not oxygen or not hydrogen. In our first half reaction, you can see that both the reactant side and the product side only have got one manganese, so there are no stoichiometric coefficients that need to be added. In the second half reaction, we have I- going to I2. Therefore, in order to balance the iodines, we have to put a stoichiometric coefficient of 2 in front of the iodide ion. In step 2b, we have to add H2O to the side that is deficient in oxygen. In our first half reaction, permanganate has got 4 oxygens, whereas manganese 4 oxide has only got 2. Therefore, we have to add 2 waters to the product side to balance out the oxygens. In our second half reaction, there are no oxygens on either side of the equation, so this step is not needed. In step 2c, we now add H+ to the side that is deficient in hydrogen. In our first half reaction, we have got no hydrogens on the reactant side, but 4 hydrogens on the product side that are coming from the water. Therefore, we have to add 4H+ to balance out the hydrogens. On our second half reaction, there are no hydrogens present on either side of the reaction, so this step is not needed. For step 2d, we now have to balance the charge by adding electrons to the more positive side. In our first half reaction, the product side has an overall charge of 0, since both water and the manganese 4 oxide are neutral species, but the charge on the reactant side is +3, since we've got 4H+ and 1 permanganate with a negative charge. Therefore, to charge balance this half reaction, we have to add 3 electrons to the reactant side. In our second half reaction, we've got I2 gas, which is a neutral species, but 2 I-, giving an overall charge of -2 on the reactant side. Therefore, we had to add 2 electrons onto the product side to get this to charge balance. Please be aware, at this point, one of your half reactions should have electrons on the reactant side, and the other should have electrons on the product side, because something is going to be gaining electrons, and something else will be losing electrons in a redox reaction. In step 3, we're going to multiply each half reaction by an appropriate integer. Since the first half reaction has got 3 electrons and the second half reaction has got 2 electrons, we will multiply our first half reaction by 2 and our second one by 3 in order to get the electrons to cancel. In step 4, we add the half reactions together and we cancel the duplicate species. As you can see here, this is our final balanced redox equation, and for full credit, you must include all states. As a final check, we want to make sure that the charge is balancing on both sides of the equation. If you add up all the charges on the reactant side of the equation, you see that it comes out to an overall charge of 0, and same thing on the product side. This is a check because in a redox equation, all elements must balance and all charges must balance as well. This concludes the second of 3 videos for the Unit 3 on balancing redox